Welcome to my presentation. This was not supposed to be a remote talk. My flight got delayed and I was stuck in London for 2 days. So I'm currently sitting in LAX airport behind the customs in the customs area and giving up my talk there. So I'm very sorry if the sound quality is not as good as it should be. So I'm going to present something which is still work in progress and which is building upon a paper that we're going to present at OOPSLA on Wednesday. This is joint work with Ingo Skupin, Tim Sübergrupp and Klaus Ostermann. So if you're interested in the paper that this is based on, just between functional programming and OOP.
Angela, please note that there is no photography.
So my working type theoretic definition of object-oriented programming is that it consists of 3 parts. One is codata types, or programming against interfaces. The second part is subtyping. And the third part is open recursion, or late binding. But in this talk, I will restrict myself to this aspect of object-oriented programming against interfaces in the type theoretic guise of codata types. And to give you some context, this is very close to some of the articles that were written by William Cook on the nature of data abstraction. So let's start with a concrete example, the Booleans in the functional programming version. So here we have a data type of Booleans, which can either be true or false, and we have the negation function, which is defined by pattern matching. So the Booleans are defined as a data type, and negations or observations on Booleans are defined by pattern matching. Here, on the other hand, we have the same program, but now we represent Booleans as a codata type with one observation, negation, which returns another Boolean. The Booleans true and false are now represented using something called co-pattern matching, which says how these Booleans behave when the negation observation is called on them. Another way to see this is that these Booleans are just implementing the negation interface. More generally, these 2 representations, the data representation, which is close to the functional programming version, and the codata version, which is close to the object-oriented style of defining types by interfaces or methods that you can call on them, they are related by 2 program transformations. In the one direction, we can go from any data type to a codata type using refunctionalization. And in the other direction, we can take any codata type and transform it into a data type using defunctionalization. This might look a bit surprising because if you've seen defunctionalization in the past, you probably have seen it applied to the function type. But the function type is just a specific instance of a codata type with one observation. So here we have the 2 programs again in the data and in the codata style. And how are these 2 types related? Well, one way to see the relationship between the data type version and the codata type version is that both programs can be represented as a matrix. A matrix which contains the canonical ways to construct Booleans as the columns and the canonical ways to destruct them as the rows of this matrix. The 2 programs are then just 2 linearizations of this matrix. And this transformation can be mechanized. So for example, here we have an example from our programming language that the paper is based on, where you can change the transformation, change the representation of a type using just the click of a button. Here I transformed the data type bool into a codata type. One of our big contributions was that we now extended this to dependent types. So here we have the same data type of booleans that we had before, but we additionally have the Martin-Löf equality type on top, and we have a proof that a negation is involutive. That is, if we apply negation twice, then we obtain the original result. This proof that negation is involutive is here written as an observation of a boolean called self, where the self type occurs in the return type of the function neg inverse. And the proof proceeds just by pattern matching on all possible booleans. If we refunctionalize this program, then we get this program where we have left the representation of the equality type as before, but booleans are now represented as a codata type with two methods: the negation and the property that every boolean that we define, that the negation method that we implement for any boolean has to be involutive. So we have these method calls where the object on which I call the method occurs in the return type of the method. And every object that I define now comes with a correctness proof. So whenever I have to implement a verified interface, then I also have to provide the proof that the implementation is correct. Just to show you that this also works in our implementation, this is the program I just talked about, where we can change the representation of a type with the click of the button. So what have we actually shown in the paper? We have presented a type theory with no built-in types. So for example, both the non-dependent and the dependent p-type or dependent function type are user-defined codata types. We have given a proof of type soundness for the system, so we do not have a problem with soundness. And we have shown that de- and refunctionalization is total and type preserving. We can also de- and refunctionalize any types that occur in indices of type constructors and which are normalized and compared during type checking. In order to do this, to de- and refunctionalize types which are normalized and compared during type checking, we have to apply some restrictions on the beta and eta quality that we can use during type checking. But I wanted to present it UNSOUND because in the related work section we have one very big open problem, which has to do with the problem of consistency. So when we started writing the paper, we started with a different title. The first title under which we submitted the paper was the proof expression problem. And the reviewers rightfully rejected that title. Why? Because the system is not consistent, and therefore we cannot say that it applies to proofs, since system is not consistent. But I want to give you an idea of what our original vision for the system is. So consider an ordinary definition of an algebraic data type for expressions, here with three constructors for variables, lambda abstractions, and function application. And consider a proof of type soundness that you would write in an ordinary proof assistant, like based on dependent types like coq or lean. So you would probably implement the substitution lemma, as well as proof of progress and preservation. So we have done this, and in a system we can refunctionalize this data type in order to obtain the following codata type. Here, expressions are defined by all the methods that we've proven by induction or recursion over the original constructors of the data type. For example, you can see that progress and preservation were defined by pattern matching on all the constructors of expressions, and you also see that we had to prove the substitution lemma, also by pattern matching on all possible constructors of the expression data type. And to show that this works in real time, so here's part of the proof of the soundness theorem, where we can just change the representation of the type, and the rest of the proof is automatically transformed. So this was our original vision for the paper, and why we called it the proof expression problem, because it applies to the expression problem in the context of proofs.
We welcome you to Los Angeles.
So we think that we are very close with our system. We have an extremely powerful refactoring tool for proof engineers, where you can change the representation of any data or codata type which occurs in a proof, unless the system is inconsistent. And by inconsistent, I mean that every type is inhabitated. We have three sources of inconsistency in our system. We use the type in type axiom. We have no checks for positivity of data and codata type declarations. And we do not implement any termination or productivity checks. So on the one hand, we could just implement what other proof assistants implement. So we could implement a hierarchy of type universes. We could check for positivity of recursive occurrences in data and codata type declarations. And we could implement termination and productivity checks, for example, by checking for a structural recursion, and that every recursive call of a function is done on structurally smaller arguments. But the de- and refunctionalized programs would no longer check. So I will now give you three examples to show why this is the case. So the first problem has to do with universe hierarchies. So I said that we currently use the type in type axiom, which is known to be inconsistent thanks to Girard and to the simplification by Herkins. So we do know that we need to introduce some hierarchy of type on universes. The problem is that that we do not know how to annotate the correct universe levels after defunctionalization. This problem has also been described by Huang and Yalop in a paper from last year called defunctionalization with dependent types. The second problem has to do with the positivity of type declarations, and can be observed in this example. Here we define a set of natural numbers with two methods. The member method, which allows to check whether a given natural number occurs and returns a Boolean, and the set union operation, which applied to a set allows to compute the union with a different set. The problem is that we have a negative occurrence of the type not set here. But this type can be the result of refunctionalizing an ordinary ACTA or COC program using only strictly positive data types. We could, for example, implement sets of natural numbers as binary trees, implement the member and union operation by induction on the tree constructors, and also implement the union operation. This program would then type check in most proof assistants like COC or ACTA, but if I refunctionalize this codata type, then I would obtain this definition, which contains the negative occurrence. This is also related to the binary methods problem from the OOP literature. And the third problem has to do with termination and productivity checking. Here we see a program that can be written in most proof assistants. We first have a data type declaration of the piano natural numbers, and we have to check that data type declaration. Next, we have to check the termination of plus. We can do this because the recursive call of plus is applied to a structurally smaller argument. And thirdly, we have to check the termination of the multiplication function, where we can assume that plus has already been proved total. So we have a natural order of declarations. We first check the totality of plus, and then we check the totality of multiplication. If we refunctionalize this program, on the other hand, then we obtain the following program. In this program, it is no longer clear how to check for totality, for termination and productivity. So how do we declare the dependency of multiplication on addition if the successor and zero are mutually recursive? We must somehow first construct partial objects S and Z for which only plus is defined. And only in the second step can we construct the complete objects which are defined, for which both the plus and the multiplication method are defined. So, yeah, it's very, very difficult, but you can follow the development of the project on our website. We have a distinguished artifact at OOPSLA, the implementation, and yes, you can also try out the examples on the website. So I thank you for your attention. I'm very sorry that, but yeah, thank you very much.
Hello, David. Hello, can you hear us? Yeah, okay. I mean, any questions? Yeah.
I'm sorry, yeah. It's super loud here, and
Okay, I have some question. There's no use of microphone. I mean, you can say the question. Say the question. Okay. Will also be answered. Okay, so thanks for the talk. The solution you hinted at of constructing partial objects sounds to me like it has to do with initialization checking, which is a problem that people in some communities have grappled with. I'm speaking too fast, maybe. So do you see any parallel between object initialization checking and your solution to the inconsistency? Any parallel between these two problems? I can take it. Yeah. Okay.
So one question I see, whether I see any parallels between object in this initialization and our solution to the consistency problem. Yes, I think the problems are closely related, but it is still ongoing work, and yes, I will be there for the entire week, so I'm very happy to chat with other people, because I think there is a strong connection between kind of verification efforts for object-oriented languages and like the initialization problem and the kind of problem that we are observing when we try to change the representation of a type. So yes, I do think there is a very strong relationship between
On behalf of Los Angeles
what we are kind of the solution we are looking for and the kind of solution that people in the OOP space are looking for.